Hi, welcome back. So we are in Chapter 6, Prediction by RCC and the outline Prediction by Classification to discuss further on the sub-outline of deep learning framework. Now we are going actually to take a further step to discuss something related to the concept of reinforcement learning. Let's assume that we have a certain environment just to represent place or space of many things are involved. So imagine if I would have one frame like that, and if you want to engage with that environment, let me say, so I bring you in from outside, the toolkit that you have some set of action that you can take for whatsoever purpose. Then we need to evaluate what is the outcome of the action that you have chosen to take, and who can decide that is the next actually environment frame. So this next guy will tell you how good your action was. There will be some kind of reward, there will be some kind of punishment, whether what you have done good or bad. Let's take an example. Imagine I have three different states. We have a state called start state, and we have another state called up state, another one called down state. So the lifetime of each frame, there is a start, and then the start goes to up, and then it goes to down. Now, to explain better each frame, it involves a transition from one state to another state. So in this particular example here, if I am at start, the next state will be up. If I am an up, the next state will be down. If I am a down, the next state will be up. So for example, let's assume that I have essential from A naught, the first one. Always the A naught will be equal to S, which is a start, then it will go up. Now in the next one, I would go from up to down. The third one, it go from down to up. The fourth one, now from up to down, and it goes like that. So you could see clearly only A naught involving this particular state of a start. To make things more interesting, as we have understood actually the mechanism of each frame involving this environment, we can create kind of episodes and number of episodes. Now each of these episodes will absolutely contain the A naught, because when we start an episode, E naught will be there at the start of the episode. Now these other transition from up down and down up down and down up, they could happen as many as I like in each of these episodes, but for fun time, let's assume there are only 5, given that the initial one has been taken. So each episode, as we said, containing the initial state of from start to up, and then after that I have 5 loops that happens between ups, down, downs, up, down, downs, up, and so on and so forth. And then once I am done, I can move then to the second one, and then I can move to the third, and so on and so forth. Let's say in each frame, state transition, 3 different actions that I'm able to do. So for example, a note 4 of selling, I can buy or I can stay. Other word to say, if we get back to our example here, when I am in the first essential frame, start, and I'm going next to up, this transition state, I can take any of these actions. I could sell, I could buy, I could stay. And once I decide on this action, then I can move to this loop of different 5 possible frames between ups, downs, up. And in each one of these, again, I can execute any of these actions. Last but not least, let's make things more interesting by introducing the idea of rewards. Rewards means if I do something right, I should be able to gain some sort of point. If I do something wrong, to be discounted with some point. So in this case, for the purpose of this example, it is clear that I have 2 important states, that's up and then down. Let's dismiss the idea from start at the beginning. Imagine now we are at the start state. My next transition is going to be up. I don't know, but I'm just telling you what is the actual construction of this environment looks like. And I was asked to take any of these actions. I'm going to execute any of these actions. Imagine I decided to say, for example, buy. Okay, this is the action I would like to take. My next state, which is going to be in this case up, will decide whether this action that I have taken at the start was good or bad. And these are, let's call them the reward table. Let's say, for example, if I have decided to sell, I am at the start, and my price then, my next step went up. This is bad. I shouldn't have done that. That's why I will be, for example, punished by -1. Say I will give myself a reward of -1. if I was at start and I decided to buy and then the price went up, that's good things. That means I would be awarded 1. I had decided to stay. Then the price went up. This is something good. So I'm going to give an extra point. Same thing let's do for the down guy here. Actually, I should be at the up because from the up, the next one should be down. It will not be from start to down directly, but will from up to down. So if I sell and the price then went down, that's something good. So I sold before the price goes down, so I would be awarded 1. And I decided to buy. And then the price went down. This is something bad, so I will be punished with -1. Finally, and then I decided to stay. Price went down. That's again something bad. So this kind of a table, it gives me a state where I am right now based on the next state, whether my actions were good enough or not. Just let's make one round of a game or two to make it clear. In the first, I start at start and then ask me what action would like to take. Say, for example, I decided to buy. Now the next one was up. If I decided to buy and the price went up, I've been awarded 1. Now I am at the up. Then I was asked what decision I would like to take. Let's say, for example, I decided to stay. And the next state is down. Now, my action at this state, it is -1. Now I'm at down and I decided to stay. What is the consequence of this action? Since the next one is going to be up, that was a good decision. So this is going to be awarded with 1. We said we're going to do this only 5 times. Once these 5 times are done, that means 1 episode of my life on this game is done. And then we can look at the first episode here. What are the total rewards that I have got? Then you move to episode 2. Now in episode 2, again, you're going to go from the start to state. Let's make things more interesting. Now you could see that in each episode, I have 5 rounds that I can go over between ups, down, down, up, down. Let's make a rule. If you decided, say, for example, to buy, and then the price went down, it's not only going to actually add this to -1, but also is going to cancel the total iteration of this inner 5 steps. So you cancel the rest and then you move to episode 3. So for example, I have done, okay, 1 here, 2, but if I hit this particular condition, entire episode is over and then I move to the next one. I hope now the idea in principle is clear. Let's now talk about some AI, machine learning, prediction whatsoever. To make things more interesting, how about if we try to create a mechanism that we can learn from what was going on before, according to this environment at the start. My next is going to be up. My next is going to be down. And between down and up, I have 5 movement. And I have to be careful not to touch this. So all these things I'm saying that it's very clear because it's a kind of sort of deterministic according to the given environment. So the environment is clear on their steps. Or bringing some guy who does not know exactly, and that's what life looks like in real actions that we can see quite clear. Can we create a framework that can learn these on its own? This is the meaning of reinforcement learning. So we could use the knowledge that we have learned so far and we can design that mechanism. Well, this is where something called the Bellman equation. Let's give a name for this guy here, Q table. For example, I am at the start. I have decided on what actions to take. For example, this action stay. There is a value here for this Q table. Let's call it 0. And we'll call this one the old value. I'm going to add the reward that I get from this action since I have come to know later that next step or next state happens to be up. Say, for example, I receive a reward of 1. This is the interesting part. I'm going to add to this the value that exists in this Q table for the next state. So I have 3 possible values based on each possible action could have been taken. So it could be this or this or this. So I'm going to look at the argmax of these guys. Now, this is called the potential earning in the future based on the available actions. Let's multiply this by some depreciation value, discount factor. Similar to the concept of discount factor, that is the current value of things that I might earn in the future. For example, if I have, say, that 1,000 in the future, it's not as valuable as today. So another word to say, today's whatever is in my hand is more valuable than what I can earn in the future. So that's why we multiply this value in the future with some kind of discount factor. Let's call it lambda. So now I have this term and I have this old value. This is perfectly okay. But if you remember from the idea of learning rate, you see, I have to learn from this particular experience. That's why we can introduce the concept of learning rate, which we discussed so many times. Let's call it alpha learning rate. And then when I do, I take this original value or the old value, multiply that by 1 minus this alpha. All this term, let's multiply it actually by alpha. Outcome of this, then we can fix it as the current value of this CQ value. Now this called the Bellman equation. And imagine after a number of episodes, these, as we said, Q values are being updated. And they should be an indicator for you to choose the maximum or the positive action here. Instead of guessing which action I would like to take, why don't I look at these values and learn from them? It's obvious that the positive of them, or the largest, is the best decision to take. This is the concept of reinforcement. And this is where a Q table can make a huge sense. But as you could see in the beginning, I didn't know anything. Everything was zero. To this end, the concept of what's so-called exploration and exploitation. When I don't know exactly, all probabilistic, I could have chosen this action, or this action. I am exploring the potential of these actions, given that next state will be like so. Exploitation means I could have a peek and look inside the Q table, and a Q table can be my guidance. Of course, if I keep exploring, I'm not learning anything, because whatever the values are in here, I'm not using them. And if I keep exploiting, that's also not so good. That's why we need a kind of a trade-off between exploitation and exploration. Let's create a condition. Sometimes I could explore, sometimes I could exploit, and this condition, it's like depreciate over the time. This is where we can introduce a concept, we call it the epsilon value, something like that. So it's the value between 0 and 1. In the first episode, we're going to start with 1. And every episode, I depreciate this 1 by small that is proportional to the time of movement. So proportional here at 0, 2, 3, 4, etc. The simplest one may be the depreciation of the actual value. I multiply 1 minus some rate of depreciations to the power of n. So what happened in the first episode, absolutely I'm going to explore. But the point is that based on what? Based on a random number, let's create another random number, okay, between 0 and 1. And then we compare this random number to this epsilon at each episode. If this epsilon is larger than this random number, then let's explore. If this epsilon less than this random, then let's exploit. This is the entire mechanism of reinforcement learning, which can give us an opportunity to look at the chance of learning. Let's see actually how we can implement this using Python. Now, in the following actually example, I have added to our notebook here is previously everything that we've learned so far on the discussion of prediction. There are two classes I have created here, a class called play, another class we call it train, okay, for reinforcement. Let's just start first of all discuss the idea of training the class. So in the train class, I have worked on the constructor here by passing up some parameters we've been talking about, because here in this first class, just we're going to create the Q table. For example, number of episodes, we're going to pass like 1,000 episodes. At this maximum step, each episode have how many possible transition between downs and up, downs and up, etc. Learning rate, the lambda or the discount factor, and then we have this exploration rate, okay, which is going to be set to 1 anyway. Then there's a maximum and minimum and decay. These are the values that decide on the value of explosion rate, which is we call it there as the epsilon. Finally, there's the exit condition that we've discussed. If I hit this exit condition, I'm going to get out. Here also I create just a word list to attach in every episode total number of words. A Qtable function, reward function. I have update function, decay function, explore function, exploit function, and finally I have got the train function. Now I created here a list which contain all these values. So for example, I have decided to train on 10,000 episodes. Each episode have 100 loop to do. Learning rate say for 0.3, the discount factor 99, exploring rate 1. So we're going to decay this number of exploration as we're moving from one episode to the other. Finally, the exit condition for now, let's say a false, later we'll say. Now first, let's create the queue table. As we have seen in the previous example, we have 3 states, start, up, down, and 3 actions. These are exactly what I have done here. I created like a simple report here to say, out of this 10,000 times, I want to make like in 10 different counts, see every 1,000 what was the situation like. So when I have done that, the first 1,000, you could see my total rewards were like 68%. I was doing good. So 68% means in 1,000 times, I have like 680 good rewarding points. So I was doing well, but you could see by the 10,000, my performance improved almost 92.10%. That means the Q values, which is returned here, I print it down for you. If you use this guide map, next time if you play, I can guarantee you 92% you're gonna win. Now, if I want to play, I just created here the play class, passed to me the Q table, which is my guide map. How many episodes do you want me to play in every episode? How many turn I have? That's all, and these are the rewards. I decide my exit condition. I decide my action, but you could see now I'm not doing no exploration. I'm just completely using my exploitation because this Q table should be good now, trained, just only 10 episodes, and I played. I am winning 555. So this is 100% winning. This is a complete model that you could see we learned from nothing. We created a model that's able to win a game. Now you can, of course, convert this into some graphical if you like to make an application of real game. You can do this in any field of finance and health whatsoever and try to see how the reinforcement concept based on that. Now there are some enhancement of that principle of reinforcement. For example, learning of this Q table instead of this iteration into guessing the Q table. How about using neural network to guess value of a Q table? Then we decide a kind of loose function, and then based on that we use back propagation to update alphas. That was all for now. Let's go ahead and actually explore further different framework given the idea of deep learning. That's exactly what we're going to do next. I will see you then.